All right, so I'm back at looking at this group here, which was multiplication over the set S. So here we could define our group as being S comma multiplication. And in this group, here was our Cayley table. So notice in the Cayley table that every row has each element only once, and the same is true for each column. So in this row column, this is the only place one exists, etc. So it's kind of like a Sudoku table. This property has a more formal name than Sudoku table, though. It's called a Latin square. So if you have a set and an operation that make a group, the Cayley table will make a Latin square. So this is a Latin square. So every group will have a table that is a Latin square. Just because it's a Latin square does not make it a group, though. You still have to fit these requirements. So there's my Latin square. Also, notice my leading diagonal here. I'm going to highlight the leading diagonal. So here's my leading diagonal. And across my leading diagonal, my table is symmetric. So I've got 1, 1. I've got negative I, sort of looking across this square, I, negative 1, I. So I've got symmetry across the leading diagonal. That's one way of seeing that my operation is also commutative. So if I have, wrong thing, so symmetry across the leading diagonal implies commutativity. And if a group is also commutative, then we call it an Abelian group. So you don't have to be commutative to be a group. If you are commutative, we call it Abelian.